Time series analysis and forecasting, Chapter 8, sections 8.1 to 8.3. So what is forecasting as far as we're concerned? Forecasting is about predicting the future, and specifically for us, it's about predicting the economic future. And the reason we want to predict what's going to happen in the future is so we can act now to take advantage of what's going to happen in the future, or what we predict is going to happen in the future. So if, for example, you can predict that the share price of Apple is going to go up 10 times in the next year, and if other people haven't predicted that, you can actually go out now and you can buy Apple shares, and in a year you're going to benefit from that when it goes up. So you can act now for something that you predict is going to happen in the future. So who actually uses prediction? Well, many people use prediction. We all use prediction, really, but let's talk about governments. Governments use prediction. Governments want to predict the amount of income they're going to get so they know how much money they could spend in the future. Insurance companies use prediction. They want to predict the amount people are going to cost them in claims. When you have an insurance policy, if you insure your home, the insurance company takes the money, but it doesn't know if you're going to claim or not, but it has to predict, makes predictions if you're going to claim, and if you're going to claim, about how much you're going to claim and about when you're going to claim. And so when they know approximately how much you're going to claim and when you're going to claim, they can actually set up their funding so they have money available to pay you when the eventuality occurs. Now they pool risk, they don't look at individuals, they look at several thousands or millions of individuals, and that actually pools the risk. But that's the main concept. Also, retailers, a retail store has to or ought to forecast. It needs to look at needs to forecast what the demand's going to be, and on staff, on products. It really needs to know all these things. So why do we forecast? To take advantage of what's going to happen in the future, in our view, what's going to happen in the future, and we can fulfill customer expectations so that when you go to the store and you want to buy a car, that car's there already. You don't have to wait for it because the car dealer predicted how many cars of a certain type, model, color, etc. would be in demand. So when you go there, they can actually meet your expectations. And customer service, that comes under customer service too. Another point of customer service is having enough staff on hand when the store's going to get busy. So you can predict when the store's going to get busy, so you can meet your customer service needs. And everything we do is pretty much to optimize our profits as businesses or minimize our costs at any rate. So that's the basic background to time series analysis. And let's move on to the PowerPoint. So forecasting methods can be classified into two categories, and one category is going to be qualitative, and qualitative is basically using expert judgment to make your decisions, and quantitative, the second way, is basically using numbers and information and data to actually make those decisions. And it relies on the historical data, and it looks at the historical data, and it tries to extrapolate a pattern from that data so it can actually push it into the future. It's actually, there's an assumption that whatever happened in the past will repeat itself into the future. So this is the idea about the extrapolation from the past into the future. And this is just saying what I just said earlier. Okay, time series patterns. What have we got here? Time series patterns. So what actually is a time series? A time series is just a graphical representation of the relationship between time and some variable, but it's got to be recorded at regular intervals of time. It could be an hour, a day, a week, a month, a year. It could be anything, but it's recorded at regular intervals. So there's going to be basically two variables involved, and one variable for a time series analysis. If we were to graph it, one of them is going to be time, and time it typically sits on the x-axis, and the other one is going to be whatever you're looking at. You may be looking at the demand for a product, how the demand changes over time. So that would be an example of a time series. Now, the actual data, to see what's going on with the data, we can actually plot the data. We can use a scatter plot, or today I'm going to use a line chart with markers. And there's different patterns we can see in the data, and we have to get familiar with looking at that data and recognizing it. So let's look at an example here. And this example is the gasoline data file, which is available to you. And what I want to do is plot this data. So I'm just going to highlight this data over here. I'm going to press insert, and I'm going to go for a line chart with markers. And this is the data. This is what we get. So what can we see about this data? Let's find out what the average is here. So the average of this data, so it's the gasoline sales. Let's have a look what we have. The average is 19.25. So what are we actually looking at? We're looking at the number of gallons of gasoline sold in thousands of dollars, sold by a gasoline distributor in some place called Bennington in Vermont over the past 12 weeks. The average is 19.25 or 19,250 because this is in thousands of gallons. And when we look at the shape here of this, you may say it looks fairly random. Where it does, it is fairly random, but it's fairly random and it's fluctuating around the 19.25. So this is 19.25 is here. So we seem to have a random fluctuation around a constant mean. And so when we have that, we have what is known as a horizontal pattern. So a horizontal pattern exists when the data fluctuates randomly around a constant mean. A stationary time series actually denotes a time series whose statistical properties are independent of time. So a stationary time series is basically the same thing as a horizontal pattern, but a horizontal pattern is the graphical representation of the data that randomly fluctuates around a constant mean. But a stationary time series is one where you prove statistically, the statistical test that you can do other than just looking at it in a graph. And once you do it statistically, you would call that a stationary time series. So this is the gasoline time series data. And here they've actually put it into the graph that I actually came up with in Excel for you. Let's look at a second example. And this is the same data for the first 12 weeks we had initially, but this gas station now manages to get itself a contract after the first 12 weeks. It manages to get itself a contract with the Vermont police station to provide gasoline for state police cars located in that Vermont area that we were talking about. So let's have a look at what this data is going to look like. I have it in an Excel spreadsheet called Gasoline Revised. So let's actually insert a line chart with markers. And this is what the data looks like. So this is the original data over here. And then what happens is after the first 12 weeks, when all the police cars are now going to this gas station to fuel up, you can see there's a big spike in the actual number of gallons sold. But the actual pattern looks relatively similar to what we had before, but at a different level. So what does that mean to us when we're trying to predict what's going to happen into the future? The change of level in this time series makes it more difficult to choose an appropriate forecasting method. So you're going to have to be aware whenever you're forecasting, if there's any blips or changes in the historical data, you have to account for them. So let's have a look at this on the PowerPoints, and that's the graph we just had in Excel. So moving on from that, what is a trend? What is a trend? Well, a trend is a general upward or general downward movement in data over a period of time. We've got some possible reasons what would cause that down here, but that's all it is. That's what a trend is. So it doesn't have to be always moving up, say. It can move a little bit down, but generally speaking, it should be moving in one direction with a few blips on the way. So let's look at an example of that. Again, you've got this available to you, the bicycle data set. And for the bicycle data set, we can actually plot that again. So let's just plot that data. And again, I'm just going to insert a line chart with markers. And this is what we get for the sales. That's what the actual chart looks like. So we can see there's a general upward trend. It's not perfect. It does come down here and it comes down here again. So that's the actual trend over a 10-year period that we see in there. So this figure in here is showing the time series of bicycle sales for a particular manufacturer over the past 10 years. We can see that 21,600 bikes, these sales are in thousands, were actually sold in year one, 22,900 in year two, and so on. And in the final year that we have under consideration, the most recent year, 31,400 bicycles were sold. So when we do a visual inspection of this data set, we see that there is some up and down movement. However, the general trend is moving upwards. When we actually look at this graph, it looks pretty good. But if we actually compare it to what we have in the PowerPoints, it looks a little bit different. And in fact, it's the same graph. This is in fact the same graph, but let's have a look why it seems different. Basically, this has a lot of empty space. So we can actually rescale that. And rather than having between, say, 0 and 20 being empty space, we can right-click here and we can go to Format Axis. And then we can say we don't want it to start at 0 and go to 35. That's what it's saying here. We want to start it at, say, for example, 20. And let's put in 20 in here. Go to 35, press Enter on that, enter that, and you see what happens there. We can close this down. And that just rescales the graph just like that. So we can actually do that. So let's go back to our PowerPoints, and in our PowerPoints we have that graph. Let's move on. And so now this is some new cholesterol drug has come out, and what they've done is that the FDA's just approved it, and we can see how the time series changes. This is the actual data, so year 1, year 2, year 3, etc. And this is what the sales are in millions of dollars. Why don't we just plot that? Let's see if we actually open up the actual spreadsheet for that, the data Excel spreadsheet called cholesterol. And why don't we actually just, again, insert a line chart with markers. And this is the chart. This is the chart that we also get over on the PowerPoints. It's a little bit bigger and clearer here. So you can actually see that the rate of increase, it's not a flat line anymore, is it? You can see that it's actually curving upwards. Okay, so it's non-linear. So we don't assume that everything is going to be a straight line or a linear pattern. This is actually increasing exponentially. And that may happen with drugs, especially if they actually start advertising them and doctors start prescribing them a lot more. They have incentives and so on. But you can get exponential growth of the sales of a drug, as you have here. Here you can see the same graph and same data on the PowerPoints. And moving on, what's a seasonal pattern? A seasonal pattern is a recurring pattern in your data that occurs or repeats over a 1-year period or less. So it can be a minute, a month, a day, but the pattern must recur within the first year, and that would be a seasonal pattern. So an example is, as it's giving us here, a manufacturer of swimming pools expects low sales activity in the fall and winter months, with peak sales in the spring and summer months to occur every year. Another example, swimwear. Swimwear is typically going to be have higher sales during the warmer periods of time rather than the colder periods of time. Snow removal equipment is typically going to have higher sales during the colder periods of time and when it snows. And so there are a lot of examples where we have seasonal data. So we actually have some data. I'll show you the next page on umbrella sales over a 5-year period. And you would imagine umbrella sales are going to be seasonal. And this same data I actually have on a spreadsheet which is available to you. Here it is. It's called umbrella. And you can see that, well, for 1, 2, 3, 4, 5 years, split by quarter over 20 periods, these are the sales of umbrellas. So let's see what the sales of umbrellas look like. And let's just insert a line chart with markers, and this is what it looks like. Make that a little bit bigger. So when you look at that, is that a horizontal pattern that we were talking about earlier, or is this a seasonal pattern? So it's difficult to spot sometimes. But here I can see there's a seasonal pattern. You can see that in period or quarter 1 and 3. So this is, if this is 1, 2, 3, let me just put some colors on that. So if this is period 1, 2, 3, and 4, or quarter 1, 2, 3, and 4, you can see for 1 and 3, you can see that the sales are moderate. And you can see for quarter 2, let's do that in a different color, you can see that the sales are at their highest, and you can see for quarter 4, they're at their lowest. So quarters 1 and 3, we have moderate sales. Quarter 2 is going to be the highest sales, and quarter 4 is going to be the lowest sales. And that pattern repeats, because again, you'll be able to see that for quarters 1 and 3 of the following year, you have moderate sales. Then for quarter 2, you have the highest sales, and then finally for quarter 4, you have the lowest sales. So you can see how that pattern is repeating. This is not always easy to spot, and I'm not saying it's easy to spot, but we're going to get better at actually doing this. And this is the previous graphs we've looked at, and back to the actual PowerPoints. Other patterns may we see? The next example is on smartphones, so we can go over and see it. So we've got a bunch of data on smartphones. This data I actually downloaded, and it is available to you in the smartphone data Excel file. And so we've got over a 4-year period by the looks of it. We've got 4 years, and we've got a number of quarters, and we've got our sales of cell phones in thousands. And let's just plot that, see what our cell phone sales look like. So we're going to insert, and we're going to go to a line chart with markers, and this is what the sales look like. So what do you see when you look at that? It's exactly what we have in right here. And it's a little bit bigger here. So what can we see? Well, we can see that there's an upward trend for sure. It looks like the data is trending generally upwards, but there is also something else we may be able to see, which is a seasonal pattern. This figure that we're looking at, it indicates that sales are lowest in the second quarter. So if this is the second quarter of each year, sales are lowest in the second quarter of each year and highest in quarters 3 and 4. So if this is the lowest in the second quarter, and then highest in 3 and 4, and then lowest in the second quarter, highest in 3 and 4, lowest in the second quarter, highest in 3 and 4. So here we actually have not only an upward trend, but we also have a seasonal pattern. And you can combine seasonal patterns and trends. You don't have necessarily just one of them. So moving on. So a cyclical pattern. What is a cyclical pattern? Well, basically, it's a pattern that takes a while to show. It typically takes more than a year to show. But it exists when a time series plot, which we'll be doing just now using our line charts with markers. If your plot shows an alternating sequence of points below and above the trend line that lasts for more than 1 year. And there's some examples of inflation and things like that show cyclical patterns. They're very difficult to spot though, I must say. So generally, what do we do when we get some data? We want to forecast it. What's our first step that we're going to do? We get our time series, and then we're going to plot our time series to see if we can actually spot any trends in it, any cycles in it, if we could spot if the data is stationary or horizontal, if it's trending upwards, and that's what we're going to try and do. Now we're going to look at the forecast accuracy. So we're going to actually use a technique here to forecast our data, and we're actually going to take the data, the original data we had from the gasoline sales. And so let me just go over to that data for the gasoline sales. So it's available to you, so it's the gasoline sales data. And what I want to do is figure out how wrong our forecast is, the forecast error. But to be able to do that, I first need to have a forecast. This is the actual sales. These are the actual sales that actually occurred for the gas station. So these are actual sales. And we want to forecast the sales and see how wrong or right our forecast is. The method we're actually going to use is called the naive technique, and some people call it the last period technique, and I'll show you why. Let me come over here. So this is week, and our first week, and this is going to be our actual sales, and this is going to be our forecast. Now, the way the last period technique works is this. It says, in week 1, we can't really make a forecast, and because the last period technique wants to figure out what happened in the last period. There's no last period to forecast what's going to happen next. So at the beginning of period 1 of week 1, I can't forecast what my sales are going to be because the naive or last period technique says, well, what happened last week? Well, we didn't have a last week, so we can't make a forecast. So we wait till the end of week 1 and we find out that our sales, let's see, what were they? 17. So our sales were 17 gallons. So now I can say, okay, what's going to happen in week 2? Well, in week 2, the only thing I've got to go on is what happened in week 1. And this technique, that's exactly what it does. It's naive and it looks at just the last period. It says, okay, my forecast for period 2 is going to be 17. So at the beginning of period 2, at the beginning of week 2, before it's actually occurred, I forecast I'm going to sell 17 gallons. And then at the end of week 2, I actually found out that the actual figures, I sold 21 gallons. So now I'll go to, I finished week 2 and I want to forecast for week 3. And my forecast for week 3 is going to be exactly what happened in week 2, which is 21. This is this particular technique. Other techniques don't use this, but this method, but this technique uses this method of the last period. What actually happened in period 3 is we sold 19 gallons. So now when I want to forecast for period 4, I'm going to forecast that I'm going to sell 19 gallons. What actually happened in period 4 is we sold 23 gallons. So there's errors here. You can see there's errors all the way. For period 5, I'm going to say, well, last period was 23. So naively, I'm going to say I think it's going to be 23 for next period. And what actually happened for period 5, sold 18. So for period 6, I'm going to say, okay, well, I got it wrong again. So I'm just going to put 18 for period 6 as my forecast or estimate. What actually happened in period 6, I sold 16 gallons. And so when I get to forecast for period 7, I'm going to go with the 16 gallons, which is what happened last time. What actually happens for period 7, sold 20 gallons. So when I get to period 8, I'm going to say, okay, I'm going to just put 20 because that's what my most up-to-date last technique, last period technique, naive technique way of doing it. What I actually sold in period 8 was 18. So for period 9, I'm going to say, okay, well, I'm going to forecast that I sold 18. And at the end of period 9, I found out I actually sold 22. So for period 10, I'm then going to say, okay, I'm going to estimate 22 because that's what happened at the last period. What actually happened for period 10 is 20. And then for period 11, I'm going to forecast the 20. And what actually happened in period 11, we sold 15. So then for period 12, I'm going to say, okay, well, I'm just going to go for 15 as my forecast. What actually happened in period 12 was 22. So how about period 13? What's my forecast for period 13 going to be? It's going to be 22. And then I can't estimate anymore because I have to wait for an actual in this cell here before I can actually put another forecast in. So that's as far as it goes. Now, that's a long way of doing it. There's a much easier way of trying to forecast what's going to happen over here. And so let's say forecast. There's a much easier way of doing it. I can start off at the bottom. I can say, okay, I know in period 12, we sold 22 gallons. So my forecast for period 13 is going to be 22. So let me put my period 13 over here. And it's going to be 22. And rather than me actually going back and filling all these in as I did over here, I'm just going to click back and go all the way back. And I'm going to stop at this point. So let me just do that again. Rather than put a formula in, I could have just put the actual number in, but that's okay. Let's put that in, go all the way back. Okay. So basically, I don't have anything in here because my forecast for period 1, using this technique, is reliant on what happened in the previous period, and there's no previous period, so I can't make a forecast. And it ends here. So as you can see, I'm wrong every single time. What actually happened in my forecast, it was wrong here, it's wrong here, it's wrong here. So let's find out what the forecast error is. And the way you work out the forecast error is by taking what actually happened and subtract from that your forecast. And that is your forecast error. Okay, so it's what actually, your error is what actually happened, so 21, minus your forecast. Let's correct the spelling here. So what's going to be here? Actual minus forecast. Well, the actual minus the forecast is 4. So what that's saying is that my error is 4 between my actual and my forecast, and my forecast is 17. What actually happened is I sold 21. So the way I could actually correct, if you like, my error is take my 17, my forecast, and add 4 to it. It's going to take me to 21. What's the next one down going to be? -2. When you see a negative sign, it means that your forecast is over. To correct my forecast, I have to subtract 2 from it to get it to the actual. So a negative sign means your forecast was over. We can go all the way down to here, and these are my forecast errors for each week. There's no forecast error in here because we need an actual and a forecast, and we only have a forecast and no actual. So why don't I find the average of these values? So the average of these values is, well, let's look, what do you reckon the average is going to be? Because we've got some weeks we're off by 4 or 5 or 7 or whatever. Let's see what it comes to. And it comes to a very small number. The issue we have here is the positive and negative errors up here are offsetting one another. And the result is really small for the average error. And that may lead us to believe that this forecast is really a good fit. I'll just correct the spelling in there as well. That this forecast is actually a good fit because we're getting a small error for it. But is that right? Probably not, and it's going to be very misleading. And the problem is because we've got our positive and negative values cancelling each other out. They're offsetting each other. So what do we do typically with numbers when positives and negatives offset each other and may mislead us? We can either take the absolute value and the absolute value, so we can find the absolute error. That's one way that we can actually do this. And what's going to happen if we take the absolute error? Well, it's going to be equals absolute of this value, and let's go all the way down. So what's that going to become? +2. Just absolute just makes everything positive. If it's positive, it stays positive. If it's negative, it becomes positive. And let's work out the average of this absolute error. And it gives us this value in here. And we're going to call this the average or mean absolute error. So the mean absolute error is just a way of measuring error. Now, some people don't like to use the absolute error. They say, we want to get rid of the minus signs. We don't want to use the absolute. What we want to do is square everything. So we're going to use the squared error. So what that means is they're going to square all the errors. So I'm going to take the error term, and which is that one in there. I'm going to shift 6, and that gives me the power key, and put the power 2. So that means I'm squaring it. So I'm going to get 16. So this is another way of getting rid of the negative signs. And if I do that, what's the average of those going to be? 16. So this is another way of measuring the error. And this one's going to be actually called the mean or average or mean squared error because we're squaring the errors. So these are two different ways of actually calculating the error, how much error you've got. When it comes to error, we want to have small error. A small error means our model is good, our forecast is good. But these happen to be two different ways of measuring the error. So for example, when we're measuring distance, and I may say measure distance in miles or kilometers or meters or centimeters or inches. There's many different ways of measuring a distance. and they're going to give you a different number. You may be measuring the same distance, but the units you use will influence the outcome of the actual number you report. So I may be traveling 1 mile, which is over how many kilometers? Maybe 1.5 kilometers or something like that. So, or I could measure that a mile in yards, and it could be or meters, it could be 1,600 meters. So the same mile can be measured in different units and give you a different value. And this is what these guys are doing. They're measuring the same error. The error is not different, but they're measuring it in a different way. And the problem with this for some people is that these units are, these measures are reliant on the measurement units. And so some people, to overcome that, they want to get rid of the measurement units being an issue. They're going to actually work out the absolute percentage error. So what's the absolute percentage error? Well, the absolute percentage error is going to be the absolute value, which is that one, and it's the percentage error, and it's going to be the percentage, the error as a percentage of what actually happens. So the error is 4, and what actually the sales were 21, and we were off by 4. So this is going to be the percentage error. It's going to be 19% for week 2. And I can copy that all the way down, and then I can actually work out the average, and it's giving me 19. I can change that into a percentage. I can add a couple of decimal spaces to it. There you go. And oh, we just changed this one. Okay, so and the actual name for this is going to be the mean absolute percentage error. So I just took I had the absolute percentage error up here, and I took the average. So these are different ways of measuring the error, and this one is not dependent in or reliant in any way on the units, because we're dividing out by the units, so it becomes a unitless measure. So these are different ways, and you have to choose pretty much which way. You can't compare these directly. I can't compare MAE to MSE I can't compare them directly, but I can make a different type of comparison. The type of comparison I can do, I can make, is I can have a different forecasting method for the same data. So this is my same data. And rather than using the naive or last period technique, I can use a different forecasting method. And for that forecasting method, I can work out, say, for example, the mean square error. So I can compare the mean square error for 2 different methods. And the one that gives you the smallest measure is going to be the one that better fits the data. So I'm going to do that right now. I'm going to cheat a little bit, so I'm going to copy this out so I don't have to do it all over again. I'm going to just copy it to here. And what I'm going to do, though, is I'm going to use a different forecasting method. Here we use naive. And the forecasting method I'm going to use now is going to be a different one. And let's see which one it's going to be. It's going to be, let me just go here, the new forecasting method is going to be the average of all historical data method. So I'm not going to use these figures to forecast with now. I'm going to use the average of all historical data. So if I wanted to forecast for this period at the beginning, if I wanted to forecast for period 2, I would forecast for period 2 before period 2 has happened. So at the end of period 1, I want to forecast for period 2. And so the forecast for period 2 is going to be the average of everything that happened. Well, there's only one thing that happened before period 2, which is that. Now, when I want to forecast for period 2, I want to take the average of everything that's happened before period 2. So I'm just going to say equals average of what happened before period 2. And so I'm going to do this. Now, I'm going to put an anchor sign on this figure in here, and I'll explain to you why in a second. So that's giving me the average of 17 and 21 is 19. What am I going to put in here? It's going to be the average of the next 3. So it's the average of whatever happened in the 3 previous periods. So actually doing this is pretty good. The way I anchored that values to save me a lot of work. Okay, and we can, if I double click on this last one, you can see it's going to be the average of all previous periods. That's why I put a $ on the B21 in this case, because it anchored everything into position. So we cheated a little bit because I actually had the numbers already set in. I had the spreadsheet formulas all set up, and I get these values. So you can see that the mean absolute error using the first technique, which is naive or last period technique, gives us a mean absolute error of 3.72. And this second method of using the average of all previous historical data gives me a smaller one. So if the measure I'm using to measure my error is the mean absolute error, then the second method seems better. If the only measure I'm going to use to figure out which of the two methods is best is going to be the mean square error, again, the second one seems to be better. It's giving me only 8.1. This was giving me 16.27. And likewise with the third one, if I'm only going to be using the third measure, the mean absolute percentage error, and I'm going to compare these two methods, then I'm actually going to go for this method down here, because again, the second method is giving me a mean absolute percentage error. So this stuff is explained in these PowerPoints as we move through. So everything here, I've shown you how it works, but rather than deal with formulas, I'm actually showing you how to actually do it. So this is the table. This is a summary table of the data we've got in here. So you can look at the 3.72, 16.7, 19.24, and you can see that 16.27, 19.24, and these ones down here is using the average past values, 2.44, 2.44, 8.1, and 12.85. So it's just these values coming in from here. So it's just a summary of what we came up with. And again, you can see when you use the naive method, so happens that all three naive methods gives you a bigger error than all three of the average of past values method. So this is best. This doesn't necessarily always have to be the case. It could be that this guy is higher than this one, and based on the mean absolute error, you should be choosing the average of past values. But it could turn out, though, that one of the other ones contradicts that. It could be it's not, but it could be that this is higher than this. It's not, as we can see. But supposing this came to 25, and that would suggest, according to the mean absolute percentage error, that it's actually going to, if this is 25 and this is 19, we should choose this method. So these methods don't have to give you consistent results in which method to choose for your forecasting. So typically what happens, people only choose one of these methods to actually measure how good their forecasting is. And a lot of people actually like to use this method in here, the mean square error method. And it actually happens to be the method that we used when we were using linear regression, and we were trying to find the best fit line through the data, and we were trying to minimize those errors. If you remember back when we did that, we said, you know, that we've got some data points and we've got a regression line, and we're going to work out these errors, this error here, and we're going to square and add those errors together. That method of least squares is the same method of this one, the mean square error method. So now we're going to move on to moving averages and exponential smoothing. I'd like to say at this point that these methods of forecasting, the moving averages and also the exponential smoothing, are both methods that are reserved for horizontal data. So horizontal data, and if you remember what the horizontal data is, it's basically data that is fluctuating, randomly fluctuating around a long-term average. Yeah, so that's what it's doing. So this is what these two methods are reserved for. And the data we're going to use to show how you forecast the future using these methods and finding out how accurate or inaccurate they are, we're going to use exactly the same data as we used on the previous example, which is the gasoline sales. So this is going to talk about moving averages. What I'm going to do, I'm going to explain what moving averages are, and I'm going to go back to the example since we're going to be using the same data. So now I'm going to change my forecast up here to correspond to moving averages. This was the naive method we had here before. So what is moving averages? Moving averages is you take the average of the last k periods. Now k is up to you. I'll tell you a little bit more about k as we move on. But if I want to take the average for my forecast of the last period, it's in fact this technique that we've got right here. Because how did we work this out? It was taking the average of the last period. It was, if you like to think of it as the average of the last period, it was just taking what the last period is doing. But when we talk about moving averages, we talk about taking the average of the last 2 or 3 or 4 periods. So if I wanted to find the moving average for my forecast here, let's delete these. For the last, how many periods? For the last, let's take the moving average for the last 3 periods. My forecast will be based on the average of the 3 periods prior to period 13. So I want to forecast for period 13, take the average of the 3 periods before that. And my forecast would be 19. And I can take that all the way to the top, or can I? Let's see. That's kind of right. There's a couple of like maybe little errors in it, so I'm getting these references. And when I click on that, I see the reason is, it's, let's just delete that because it's so obviously wrong. And delete this one. Is this one right? You always have to check, and the answer is no, it's not right. If I'm trying to average over the last 3 periods, I need 3 periods worth of data. And I've only got 2 periods worth of data for this formula. So this one can't work. I'm going to have to delete that. Does this one work? Yeah, it's the last 3 periods. So remember, to work out the errors, you need to have an actual and a forecast, so we can't work it out for these over here. So this is how quick you work out the forecast for a k period moving average. This is the 3 period moving average. And you call it a moving average because it's the average of those 3, and then it's going to be the average of the 3 above, and then the average of the 3 above that. The average keeps on moving. So that's why they call it a moving average. The fewer periods you average over, the lower the value of k, the more responsive or the more changeable, the more volatile your forecast will be. So that's basically all it is. And what I can do there is to show you a couple more things on it though. I can start off by showing you the actual curve of this forecast. So I'm going to put the actual data and the forecast data, and let me insert, and let me go to a line and with markers, and this is what it looks like. So the reason the forecast starts a bit late is because we've got this missing information here. And you can see it's a lot smoother curve than the blue curve, than the original data. The larger the value of k, so if you average over more and more and more periods, the smoother the curve becomes. The smaller the value of k, so you average over, say, only a couple of periods, the more volatile or rough the curve becomes, the more responsive it becomes. So you're probably thinking, is there a way in Excel that I could have actually worked these guys out over here for the forecast? And the actual answer is yes, there is. So what I'm going to do is I'm just going to insert in here a column. I'm going to show you how to do it. So you're going to hit data up here and data analysis over here. And we're going to go to moving average. So scroll to moving average until you find the moving average. And once you find the moving average, let's have a look. Click on that. And so this is the range of my input. And I haven't included the labels. I'm not going to click on labels. And my interval is 3. The interval just means how many periods are you averaging over. What is k? K is 3. We're averaged over 3 periods in this particular example. So 3 goes in here. And I want the output range to go here. Oh, is that right? Yeah, it is right. You always have to offset your data by 1 for your output. So your output has to start 1 below. It's a glitch in Excel. So you press Excel, OK, over here. And look, we've just reproduced all the same numbers as we came up with by using the formula ourselves. We just reproduced all those numbers. And we already worked out the forecasting error measures down here. They're already worked out. And the way you may be thinking, how do they choose k? Do they choose k to be 3? We chose it to be 3. Why didn't we choose it to be 4 or 5? Well, what people do a lot of the time is they're interested into finding the mean square error. So the mean square error, when we use averaging over 3, when we use k equals 3, is 10.22. And then they're going to use trial and error and say, let's make our forecast be averaging over 4 periods. So they put it over 4 periods and they run through and they find the mean square error. And if the mean square error is better when you average over 4 periods, so better, I mean if it's smaller, you want a smaller error. So if the error is smaller when you average, say, over 4 periods, then you know that your forecast is better using k equals 4. So they use trial and error. They use k equals 2, 3, 4, 5, 6, 7, 8, 9, 10. They use different values to average over. And for each of those values, they work out the mean square error. And then they're going to choose the value of k that generates the smallest mean square error. So the moving averages method we've just looked at, and if we can actually look through your PowerPoints here, and they actually go through what I just went through on the spreadsheet, shows you the diagram, shows you how to use Excel and come up with the solutions, and also how to come up with the forecasting errors using the 3 different measures of mean absolute error, mean square error, and mean absolute percentage error. And those figures should all match up with what we have. So there's another way that we can forecast data, which is stationary or horizontal. And that method I'll show you just now is actually called the exponential smoothing method. And what I'm going to do is I'm just going to delete this from here. I'm kind of using this stuff as a template. I can update my forecast to put whatever I want into here. So if you want, I can delete that. But what is this method that we're talking about that's called the exponential smoothing method? Well, this is what it's based on. It says the forecast for, say, period 13, the next period, is equal to the forecast for period 12. But probably you made the mistake when you're doing the forecast for period 12. So we have to add in alpha times the amount of error you made. So it's kind of correcting the error. So this is the forecast you put in right here, which is probably wrong. And the error you made was the actual in period 12 minus the forecast from period 12. This amount is the error that you made. So it actually is going to add back part of the error. It's going to add alpha % of the error. And alpha is actually called a smoothing constant. So this is called a smoothing constant. And it is dictating how much of the error you want to add back in. Now, there's a trial and error approach to coming up with alpha that you can use, which I'll speak about as we move on. But suffice to say for now that alpha will take a value which is going to be a maximum of 1 and a minimum of 0. So you're adding in between 0 and 100% of the error that you made. So if we want to calculate the forecast for period 13 here, how are we going to do it? So let's say when the forecast for period 13, the forecast for period 13 is equal to the forecast for period 12. Oh, can't do it because we don't have a forecast for period 12. Oh, that's okay. What we'll do, we can use this formula again. What we'll do is we'll say, well, we need the forecast for period 12. So let's just do that. The forecast for period 12 is going to be equal to the forecast for period 11, according to this formula, plus alpha times the actual for period 11 minus the forecast for period 11. Now, the problem we're going to get right now is because we actually don't know any of these forecasts coming into here. So eventually we're going to have to go all the way to the top. That's what this basically means. So we're going to have to start the forecasting from the very top level up here. Now, when I'm at period 0 and I want to forecast my sales of gas, gallons of gas for period 1, if I'm basing on historical data, I can't do it. So this guy's going to be a blank in here. How about in here for period 2? Well, this is not really going to work properly for period 2. So I have to look at what happened in period 1. I need an actual and a forecast for period 1. This is still not going to kick in. So all I'm going to do for period 2, I'm going to say, look, in the absence of any other data, I'm just going to put in my forecast for period 2. I'm forecasting at the beginning of period 2. Before I know what actually happened in period 2, I'm just going to put the forecast for, the actual for period 1 as the forecast for period 2. Now, when I get to period 3, I can actually use this formula. This formula says the forecast for period 3 is equal the forecast for period 2 plus alpha times the actual for period 2 minus the forecast for period 2. And I actually know all that data. I know the actual for period 2, and I know the forecast for period 2. So I can do this calculation. Now, for the moment, let's just say that alpha, let's put it in here. Let's just say that alpha is equal to 0.2. We'll discuss that as we move on. In a way, it's saying I want to correct my last year's forecast by taking 20% of the error into account and adding it back in. That's what it's basically saying for now. So how would I actually do this? Use this formula. So the forecast for period 3 is going to actually be equal to the forecast for the previous period of period 2. So it's going to be the forecast for period 2. And from that, I'm going to add in alpha, which we said is going to be 0.2, multiplied by the difference between the actual and the forecast for period 2. So it's the difference between the actual and the forecast for the period 2. And that's what the forecast is going to be. And in fact, you can see this formula. I can actually copy it all the way down, and I'm going to do that right now. I will copy this formula all the way down, and that gives me all the forecasts all the way down using this method. And there you go. And instantaneously, we get the mean absolute error, forecast error, the mean square forecast error, and the mean absolute percentage error as well. So let's actually see. I think we've already done that here, but let me delete that and do it one more time for you. Let's actually show what the chart looks like. So let's insert a line chart with markers, and you can see. So this is actually smoothed everything out for us. The forecast look is that red line looks very smooth as compared to the original data. This is the original actual data in blue. So this is why we call it smoothing, because you're smoothing things out. One thing I'll tell you about this method is that the way it actually works mathematically is that it actually is a weighted method. It takes a weighting of all the previous data, but as you move back in time, those numbers are worth less and less. They're counted less and less. This is inherent in the method. So whereas we looked at, say, the 3-period moving average, it was taking the last 3 periods and giving them equal weighting. It treated them equally. This method takes all previous data into account, but as the data gets older and older, as you move back in time, it gives it less significance and it gives it a smaller weight. So this is pretty much how the method actually works. I can also show you, I can show you how to actually get those figures directly from Excel. And to do that, I'll do that in a second. But it's good to know that the smaller the value of alpha, alpha is only 0.2 or 20%. The smaller alpha means that your data will be more smooth. This red line will be more smooth. As alpha increases in size towards 1, then this red line would become more responsive to, we'll call it more responsive, more volatile, seems more aggressive. So that doesn't determine how you come up with alpha. That's just a by the by. So what I'm going to do right now is actually show you how we could have actually come up with this forecast just using by data analysis in Excel. So let's hit data up here, data analysis over here, and there's something called exponential smoothing in the drop-down menu. Press OK, and we're actually going to put in our data in here. And the thing is, it doesn't ask what your smoothing constant or your smoothing factor is. It actually asks you for something completely different called a damping factor. So what is the damping factor? The damping factor is 1 minus your smoothing constant. So because alpha is 0.2 for us, the damping factor we put in here is 0.8. And when you put the output, I'm going to actually put the output right in line with this. I don't have to offset it by 1 as we actually did before. Let's press OK. And we get exactly these same numbers as we have over here. The only one, there's one missing, which is the last one. Now I can add that in by dragging the formula down. But be careful, if I just drag down like this, Excel will give me the wrong number, okay? Because it's trying to find a sequence in the highlighted numbers. So I have to click just on that number and click and drag that down to get the same number over here. So other than that, the other important thing I'd like to say right here is how do you pick the value of alpha? typically what people do to pick the value of alpha is they use trial and error. So what they'll do is they'll put alpha equals 0.2, and they're going to go through this and they're going to work out the mean square error. And when alpha equals 0.2, the mean square error is 9.4, the measure of error. And then they're going to try a different value of alpha, like 0.3, and they're going to work out the mean square error. And then they're going to try again a different value of alpha, trial and error, of say 0.4 and then 0.5. And each time they're going to work out the mean square error. And the value of alpha that gives them the smallest mean square error is the one they will go with. That's just one method of actually doing this.